Greetings engineers. In this presentation we'll cover the design features of STAAD.Pro based on the Australian AS4100 steel design code. So we'll do some basic modeling. I'll show you how to form physical members, how to apply properties, loads and automatic load combinations, P delta analysis, and then specifying some design parameters using the physical member mode, and finally code checking. Okay, let's get started. So this is the model which I'm going to show you today, right from the scratch. You can see it's a simple space frames with two secondary beams, the end releases and cantilevers, and then we have tension-only bracings. So let's get started. For reference, I'll keep this model side by side. So I'll open up another session of STAAD.Pro. Okay. There are various ways of creating this model. The easiest way would be the first method, which is using the grid. Notice that our structure is having a height of 4.5 meter. By default, the grid is 1 meter spacing. Either we can change it to 0.5 meter increment, or it doesn't matter, we can model it as 4 meter, and then the length as 7.5 meter. We use 7 meter. Then very easily here I can change the height to 4.5 meter, or I can just move this beam to 0.5 meter and then move this column to 0.5 meter in the x direction. Okay. So you can see here, I forgot to link the beam, so just redoing it. No retain connections, 0.5. So this is very important. Okay, so now we got the required dimension of 7.5 meter by 4.5 meter. Okay, so elevation view, isometric view. Most of the time I switch between these two, and sometimes plan view. Okay, now I split this beam into 3 segments. So I use 3 points. I split it into 3 segments, meaning I need to insert 2 points. Okay. So then we got 3 segments of 2.5 meter each. Okay, so now I'm going to repeat this in the z direction one time with a spacing of 7.62 meter in the z direction. You can see the axis here, the bottom left side corner. 7.62. Link steps, open base, so that I don't need the linking at the bottom. That's it. There we got our model. Okay, and the bracing, I just need to connect it just like this. Okay, finally, property. I just use the Australian sections. UC for the columns and UB for the beams, and maybe angles for the bracings. Okay, so let me choose the UC 310. And then I had a single angle of 75 by 6. Now I start assigning the sections. if you have any other beams, for example cantilevers, I forgot to add them, so select these joints and copy it and paste it at 1.5 meter. Then link them. For this cantilever beam also I apply the same beam section, UB310. And I'm going to apply some member releases. For both start and end. So you can see the hinges here. Okay, and then I'm going to apply some support. In this case it's spring support. And coming back to the specification, I need to apply the tension member parameter for this bracing. Align to this. And loading. First I use dead load. Apply the sulfate command. Maybe some UDL. And next, live load. Apply a flow load for this, say -2 kN per meter square. Here I specify the range, and here I can choose it as one-way distribution. Here you can see the flow load is getting distributed for all these beams, one-way direction. Okay, next I need to apply wind load, so I go to the definitions of wind load. Here. Apply a wind intensity of say 1.5 kN per meter square to the full height of the building. Use exposure factor of 1, and now I can start applying the wind load. Okay, so first I'll apply in the X direction, and this being open structure, I can click on this button, and I don't need to specify this except the X range, so that it will be applied only to the left frame only. Same way I am applying for the wind load in other direction. Okay, so wind load is now applied. Now I need to do the load combinations. You can see I have added Australian loads here. It's very easy to add our own loads by using this loading edit auto load rules. You can hit on this new code and type in Australian. You can see here I created a new code Australian, and category as AS in New Zealand 1170.0, and then I filled up these values. It's easier method is to copy the similar code which has a British code, and then you can modify those values to suit the Australian code and update the table. That will be permanently remaining in your computer, so you can use it for other projects also. Okay, so now that I showed you how to create the load combination code, let's use it and create these combinations automatically. And these combinations, I want to create them as repeat load cases so that it will be useful for my P delta analysis as well as my tension members. Okay. And if you want to include the notional loads, you can click this button. So I have created the load combinations now. Let's quickly go to the analysis, and I specify the P delta analysis converge command, and design. Here I choose the Australian AS4100. And the design parameters, to go through it one by one may take time. My suggestion is to suggest the users to read this International Design Codes Manual, Australian codes, and Steve Designers by AS4100. Please go through this design parameters page. And here you can see the default values for, as well as the description for each and every design parameter. In today's presentation, I'll be specifically covering this p-brace command. As you can see, it's valid for only physical members, and this command is specifically introduced just for the Australian code. And many other parameters you can see in other codes. Whereas p-brace is unique for the Australian code. Okay, so before entering the design parameter, one thing we should do for Australian code is forming the physical members. It's very easy to form the physical members. Just select all of the members, then use auto form member. Program forms the members automatically, but I want to modify this automatically form the physical members just for these two beams here, this one and this one. It's because of this cantilever. So I just delete those physical members which are automatically formed, and I'm going to manually form the physical members by choosing the analytical member cursor, selecting these three members as well as this three members and forming them separately. Then this member separately, this member separately. So I finished forming the physical members. Now I can enter the design page, steel design page, and choose the Australian code. And directly we can go to the physical member free brace command. Before going to this command, there's one important icon that we should click is toggle to physical member mode. Okay, this is very important for Australian code. Okay, and then select this physical member cursor, and then go to define parameters and specify the p-brace command. Okay, so this p-brace command I'm going to use specifically for these two main beams as well as these two cantilevers. So first, my pre-brace location at the end point here and here will be fully restrained, and the bottom flange also is fully restrained. Okay, and then at this location we need to calculate that factor. Actually, it is 7.5 meter, 2.5 meter divided by 7.5 meter. So 0.33. So 0.33, we'll have a lateral restraint, that is this secondary beams here, and the bottom flange is unsupported. And then 0.67, that is at the second point, we again have a lateral restraint. The bottom flange is unsupported. And at the end, here we are expressing the bracing location in terms of a factor of the length. So they are not lengths but as a factor. Okay. So at the end it is fully restrained. So now you can see this p-brace command is added here for both top flange as well as bottom flange. Now you can select this physical member cursor and assign them. Okay, and then specify the ultimate tensile strength of the steel or the yield strength of the steel. So assign to view. Notice that when we are in physical member mode, this physical command is getting added. Okay, so it's very important that you should be in the physical member mode. Okay. Now is the length in local y, Ly as well as Lz. This is useful for the slenderness ratio calculation, hence the compression and tension capacity of the members. So the length of this unsupported length in this direction is 2.5 meter. So if you can look at the labels and look at the beam orientation, you can see the local axis orientation. The blue color is the local X, the red color is the local Y, and the green color is the local Z. So first we need to specify the unsupported length in the local Y axis as well as Z axis. Okay, about the local Z is 7.5 meter, and about the local Y is 2.5 meter. Okay, so I use Ly as 2.5 meter. So we can specify this to this member and this member. And then Lz is 7.5 meter. Okay, for the rest of the members, we do need to specify the effective length values because the default value of the member length is good enough. And I forgot to specify the unsupported length for the, the P-brace command for the cantilever. We can do that now. So P-brace for the end 0, that is fully restrained for both top and bottom flange, and the other end is unrestrained for both, being a cantilever. So we can now assign this to this member. That's it. Okay, we can verify this commands one more time. Okay, and finally, to get a elaborate output, I'll set this track parameter to detailed. Okay, now we should use the check code command. That's it, and finally we can check our input by going through this input file of STAAD.Pro. It's very user-friendly text commands. So at one locations we can go through complete details. It's very useful for checking as well as editing. Okay, I forgot to add a command to perform the design only for the load combination, the critical case for load combinations, which I can enter it here. Load list 5.2. The same command could have been added using this load list, using the graphical user interface also, like this. Both would have produced the same results. You can see the load list which I added graphically. I'm just adding the command here, whereas I should have been added it here. That's why the editor is very useful to type in the commands quickly and at the exact location. Okay, now let's clear our model, switching off the beam orientations and the member numbers, physical member numbers. And note that by switching on this physical member number, we can see the lateral restraints and for both the top and bottom flanges. You can see the top flange and bottom flange fully restrained at the end, and here is laterally restrained at the top flange and unrestrained at the bottom flange. And let's look at the cantilever, so which is unrestrained at the top and bottom, the other end, and the fully restrained on this end. Okay, we can also check our specifications in a model. You can see this, these members are assigned as tension members, and that's why I created the load combinations as repeat load cases. Okay, repeat loads are just like any other primary loads. Okay, now I should perform the analysis. See 0 errors and 0 warnings for 15 nodes. Let's have a look on the nodes. Okay, it gives a mild information to the user that if you use flow diaphragm command, then we should use the wind load definitions after the flow diaphragm definition. But in our case, we don't use any flow diaphragms, so we can ignore this node. The other nodes are about the tension compression command convergence. Okay, so all our tension compression analysis is converged for all our load cases. So you can see totally there are 13 load cases. That's 4 primary load case, and the remaining are combinations created as repeat load cases. Okay, so now that we finish our analysis, let's go to the post-processing and check our results. Maximum reflection is 9 millimeter. This occurring here. We can enlarge our reflection diagram by using our control key and middle mouse scrolling button. I switch out the labels. You can see more clearly, and we can plot the results for the node reflections. And if you're not interested about all the nodes, we can look for the node which gives the maximum result as 12 node number 12. So results view value for a range of only node number 12. So that gives the reflection of the maximum node only. And then we have support reactions, and we can customize this table for the support reaction to select whatever load case we want, and we can bring this to spreadsheets. We can sum up all our vertical reactions. 54.12 is the total bed load, which you can verify with the static results. 54.119, rounding after 2 digits is 54.12. Okay, next, bending moment diagrams. You can view the results values for all beam results, either the maximum or midpoint or end point or all together. To be more clear, we can cut sections like this, and we can view in separate windows. We can also view the stresses in 3 dimensions. You can move your cursor. You can see the compression flange is in red color, and tension flange is in blue color. As you scroll through this cursor, you can see this stress in 4 corners of the beam. And the unity check ratios clearly shows me these 2 beams are failing, and the ratio is 1.021, meaning if we can slightly increase the beam, that should be okay. Beam size, slightly increase it. So instead of 310 UBC, let me choose the next higher size. This is the one we are using now, so I use the next. Rerun the analysis. check the results. Now it's all okay. There's no failed messages. You can also view our results in the output file. There you can see elaborate step-by-step calculations for each member. And this detailed report is created because we used the track parameter set to true, giving us elaborate calculation results for each member. Okay, here you can see the critical segment subsegment design is required by Australian code. It is done here, and for exporting to say microstrand users, you can export the STAAD.Pro model into ISM, and then in the microstrand latest version you can import it. This way you can round trip the model between these two programs. Even multi-frame also the same. Okay, hope you enjoyed this presentation of a simple space frame model analysis, modeling analysis and design as per AS4100.